Let's get started on the next session. So thank you everyone once again for joining. This will be the first hands-on lab about the controller setup and configuration. So let's dive into it. So this is the overview of what we'll be talking about today. So before we begin, what are some prerequisites? Second of all, will be file configuration. We've talked about this before. It will be which device, the JSON file you need to create your address maps and control maps, and how to upload them to the controller. And then the third one is success. What's next? And there will be some time for Q&A if possible. Okay, so before we begin, prerequisites. So I have my local hardware set up here. It's the controller powered with a 24-volt power supply, and it's connected to a network switch and is available on the default IP address, which is 192.168.1.10. So every controller ships with a default IP here. And then what I also did prior to this lab is I uploaded the software, or the firmware is updated to the latest version. I uploaded the PPL application, also the MQTT broker is installed, and I made sure that the license is added to the controller as well. So I'm talking about all of this, but all these things that I just talked about, you can find in our online documentation. Let me open it real quick. So this is the online documentation that we've prepared as well. It's available online and for you to watch. You can go to directenergypartners.mintify.app. So all this installation, login, networking, credentials, firmware update, and app installation is all explained here. So how to connect to a 24-volt power supplies explained in here. How to update the firmware to the latest version is also explained in here. And going through these steps, this will get you up and running in less than 20 minutes. Okay. And then, of course, how to request a license and update a license to the controller. So this is what I've done before. What I now want to focus on more is the file configuration part. Let me go back to my slides. So for the file configuration, there are some steps that we need to do. So step one is for repository. So we've created a public repository available on GitHub. Like Giel already suggested, GitHub. Why we use it, or why we want to use it, is first of all version control, and also you can collaborate with your team members on the same repository, so no need to exchange files. So two major advantages of using GitHub repos. So you can go ahead to that online PPL based repo, fork your own, and create your own copy of that and start from that one. And then you can start changing these files, add new files, add new address maps, and so on and so forth. Second step that we're going to do is update the devices.json file. This is the file that holds all your devices, being a battery, a converter, solar optimizers, even your pre-charge circuits or pre-charge contactors are in here. And we need to fill in the right parameters for each and every device. More on that later. Step 3, create the address map. So once we've added a new device, that one comes with a address map as well. So we'll create a JSON file for the particular device that we're adding now. Why JSON structure? Is because it's a unified structure, easy for management. That's why we use it. And then step 4 is create the control map. So the address map and control map go hand in hand. This will be made more clear once we actually get to the control map. And you can see the control map as actually a map that with just one single command, you can send multiple commands into one command to your system. For example, when you want to have a startup sequence, you can send multiple commands to your converter, for example. And then step 5 and 6 will be link the repository to the controller. So there are two options here. With a controller that's connected to the internet, you can use a git pull to pull your changes onto the controller itself. And when your controller is not connected to the internet, there is also a manual upload available using FileZilla or WinSAP or any secure protocol to upload your files to the controller. And then, of course, we'll conclude with a small test application. Okay, so let's dive into it. So let's start with forking that repository. So let me go to that repository here. So it's online, it's hosted by Direct Energy Partners, but you can go ahead and go to this website and start forking this repository from where we will be starting. So for example, give it your name, it will be stored under your personal account. Of course, you need to create a GitHub account, but it's easy to set up. So then you can create fork, and it will create that demo fork or copy of the PPL base repo onto your own GitHub account. And from there on, you can start modifying files. I would prefer using a code editor like Visual Studio. Personally, I'll use Windsurf to do my codings. So any code editor will do. So next thing that you'll need to do is, of course, clone this GitHub repo that you just created to your code editor. So let me open a new Windsurf. So if you open your code editor, same holds for Visual Studio. So you can go to clone repo, you can copy and paste your personal link in here, and you can clone it, and it will do this for you. I already did this before, so I'm opening it now right here. And this is where you start. So next step, we're already at step 2, is we'll modify the devices.json file. And in this lab, what I wanted to do is add a new converter to the repo. The converter will be a 30C3 stability from CE+T. Why? It's because I also can test with it here in our lab. It's currently set up here, so I can interact with it and check the actual status of the converter. So we'll start with the device.json file. Here's already a device added. It's a battery. So let's go ahead and add a second device, which will be our converter. For simplicity, I will just copy and paste the device from the battery entry and modify the ID, type, protocol, and all other parameters here. So let's name this new device. The ID is the name of the device. Let's call it converter1 in this case. For type, we'll type in a converter. It's a converter. This new device, so this converter will also be communicating to our controller over Modbus TCP/IP. So both the controller, the battery, and converter are all connected to the same network switch on the same network using Modbus TCP/IP. For the IP address, we'll type in another one. So our converter is at 192.168.1.21. And for port, it's 502. Slave ID in this case is at 240. So these are all required parameters that you need to fill in if your device is using Modbus TCP/IP as a protocol to communicate. Then, of course, we need to add the control map and address map. So we'll add that, but the names that you're going to give your control map and address map, you should enter here under control map and address map. So they're already here in my repo on the left-hand side. So the control map is control 30C3 underscore control. And the address map is called 30C3 underscore address map. And disabled, we'll set it to false because we are enabling this device, so to speak. So this is the first step, device.json file. We have a battery added here. We have a converter added here. in the end, in the last step or step 5, we'll upload these files to the controller, and then the controller can start interacting or interfacing with the devices. Next thing is, once we've, of course, maybe I'll need to add here. So in this device.json file, you can add more and more devices as you go. So you can start with one, start testing it, and start troubleshooting it. But of course, you can add multiple converters, multiple batteries in here. Even your pre-charged circuits can be added here as well. So this is where all the devices live in the devices.json file. Okay, next up is the address map. So we'll go ahead and define the address map for the 30C3 converter that we're interfacing with. So you see right now it's still an empty address map here, but we need to define it. For that, I will bring up the address map guide from the actual converter, and I'll do a split screen here. I hope that is okay. And what we now want to do is add our registers in here. It's a pretty long list of registers that I need to add. So as an example, I'm going to add a couple of them so that you have a feeling of what it looks like, how easy it is to add these registers to the address map. And I'll also at the end will show you how that finished address map will look like. So let's start with this one, the P1 control method, which is at address 65. So if the controller reads or write, it's a register that has both reading and writing access. So as soon as this register is defined in the address map, the controller can, or in our own application, can use this command to actually change the port method of this actual converter. So let's go ahead and add this register to the address map here on our controller. So these are some prerequisite or required parameters that we need to fill in always, which is the address, the number of registers, the name of your register, the data type, and the function code. So because it's a Modbus TCP/IP, it comes with function code. So 1 to 4 for reading, and 5, 6, and 15 and 16 to write registers. So let's go ahead and add this first one as a measurement, so like a reading. And second of all, we'll add the same register as a control. So what we need to do is change the address to 65 because this register will be available on register 65. The number of registers is still 1. And let's give it a name. We use the convention for all reading registers to use the prefix measure dot. This is something that we do internally to keep things simple, to make it clear what a register is to measure a certain register and what the register is to control a certain register on the converter. So let's start with measure.ports.port1 method. This is the name that we're going to give it, and then data type, it's a hex, and in this Modbus guide you see that the hex is a UN16. I can go to it real quick if I find it. So hex is a hexadecimal 16-bit value, so it's a UN16 in this case, not assigned, but a UN16. Let me go back to that 65 register. Okay, and then since it's a reading register, so we have function code 3 in this case. We're not done here yet. We have to add another optional parameter here, which is the mapping function. And what the mapping does is, in this case, you see that this register has certain values that it will spit out. So either 0 indicating your control method is, or your port is set to idle. 1 is meaning that your control port is set to net. Same for G power and for F power. So what we do is add the map and type in the type of the map that we're going to add. In this case, it will be a value mapping. So not a bitwise mapping. We have two options available for mapping. So a value or a bit mapping. Bit mapping is what it means. So every bit represents a certain value. And value is the register will read or give back a certain value, and that value corresponds to a certain value or state of your port. And then it's a matter of adding all your ports in here or your values in here. So one is the idle. The one is the net mode. Then the 402, it's expressed in hexadecimal. If I'm not wrong, that should be 1026, which is the G power. So our control always handles things in decimal numbers, not hexadecimal. So that's why I'm making the conversion here. And then the last one, 502, is the the F power. So this is the first register that we set up. This is complete. And now move on to the second one, which I said this is a register that has both a read and a write. So what I'm going to do is copy paste it and make sure and just modify some of these parameters in here such that it becomes a control register too. So what I need to do in order to do this is change your name, and same convention here, measure for reading, control for writing a value. So we change the name to control ports, port one method. Number of registers stay the same, address stays the same as well, and your data type stays the same as well. The only thing that I need to change here too is your function code. So now we make sure that this register can be written to the converter. So these are our first two registers that we've added. Let's move on to another one. So you see there are a lot of registers here. Let me pick out one that is also useful to implement is, for example, the voltage on the port 1 on the AC side of this converter. So it starts at register 109. It's a data type voltage. It's read only, so we don't need to add a control value here. So what I'm going to do is just copy paste it. I'll remove the map because we don't need that. And we'll add it here to the address map. So it's register 109. We only need to read one register. For name, we'll change it to measure the port 1 voltage. And since we're reading the voltage between the A and B line, I'll add voltage.AB. Data type is voltage. And what voltage means in this case, which we can find in the address map as well, a voltage is a signed 16-bit integer. So instead of a uint, it will be an int16. Again, it will be a reading register, so function code will be 3. Let me go back to the 109. And that's it. There might be registers that also need scaling or an offset. So for example, you can add a scaling of 10, a scaling of 0.1. But in this case, since this register reads back in units of 1 volts, this is okay. So we like to use SI units to represent all these values. So in this case, I don't need to add a scaling value. Scaling is set to default to 1, and our offset is set to 0 by default internally. Maybe let's also do the 1010 and the 111, which is also the voltages, but on the B and C arm and the C and A. So easy to do here is copy paste. So it's the 110. Address measure port 1 voltage, but in this case we'll have the BC flag in here, and that's it. And same goes for the third one. So this between the C and A. So we'll add it here. We'll change the add registers as well. Let's do a couple more, which is the 119, which I selected, which is the power. And the interesting here is that we'll have a scaling as well. So the power, the real power at register 119 with data type power, which again is an in16 read access only. So easy to do that. Copy paste my previous one. I'll change the address to 119. I don't have to change the data type. The only thing that I need to change is the name of the register. And then, like I said, this register reads back in units of 10 watts. So if this register reads back a value of 1, that actually means 10 watts. So what I want to do in this case, since I'm using SI units, I'll add a scaling of 10 in here. So that way it scales automatically and you don't need to do any conversion anymore in your own application or whatever. Okay, let's do one more. It's a control and a measure register. Can be interesting to control a voltage set point. So register 134. So where we want to set a voltage set point to port 2 of the converter. Same thing goes here. We'll start with the measure or the read register here. So let me go ahead and copy from the above and change the address, name, and scaling if needed. So the address in this case will be 134. We're still reading only one register. For naming convention, we'll say measure the port 2 in this case. And measure ports and we do the voltage. So this reads, or we can add a set point because the actual voltage and the set point might differ. So let's call it measure ports port 2 the voltage set point. Again, it's a voltage type which is an in 16. And we don't need to apply scaling in this case since the register is reporting the units in 1 volts. And then one more thing is we'll define the same thing, but for the control register. So we'll use the same address, same number of register. We'll change the name to controller port 2 voltage set point. Data type can stay the same. Only the function code is what we need to change in this case. So these are a couple of registers to give you a feeling of what it requires or what it takes to move over from a PDF file that contains your all your registers of your device, moving it over to the address map that can be used on the controller and that allows the controller to interact with your converter. There is one more thing that I want to show you here as well. Another register that is really I wouldn't say important, but it's really useful because probably some of you know is that Modbus. With Modbus, you can read multiple registers at once, so it's more efficient than having to pull all these single measure registers individually. That's time consuming. Your Modbus server and your client will get overloaded. You'll get timeout issues. So what Modbus also does is well, we call it a multi-read. So you can read multiple registers at once. So the maximum Modbus can read together is 125 registers. So that's what I'm gonna do here as well. So I'll start from address 65. And what I'll say to this first register, I want you to read all these registers all at once. Let's call it a name and say, this is my measurements 1 register. It's a function code 3, so it will read. So what will happen here? One thing that I need to add is the multi-read parameter here and set it to true. So what it will do is once you call this register, it will automatically do a bulk read of 125 registers in this case. And we've built a software so that, or the controller OS, so that it will map all these values to the correct register that you have over here. So you don't need to take care of mapping these registers to the register that you just defined. Know that the controller will take care of that. This is especially interesting when you have lots of registers that you want to read in this case. This is it for demo for the address map. This is not a complete one, but I have the complete one here as well. So let me migrate that over. So this is this is the starting point, but in the end, this is what your finalized address map can look like. So we have 1,500 lines of code here. It looks time consuming, but once you get started, this is pretty easy to set up. So we have all our registers defined here. You see your multi-read registers, you see registers to monitor the faults, you see registers that, again, control the same port method like we defined just a couple of minutes ago. Power limits, current limits, it's all in here in this address map now. So, and once you define it once, you can reuse it in any other site that you have. So set it up once and just copy and paste it to any other GitHub repo or another project that you have, and you're good to go. Okay. So that was step 2. Now we'll proceed to step 3, which was creating the control map. This is going to be much easier in this case. I mean, it's not so overwhelming as creating the address map, but the control map, like I said before in my introduction, it's more like combining registers that you want to send to the converter in this case all at once, rather than having to continuously have to call all the registers that you want to read or write. And the most important one in your controller.json file is your measurements. So we'll periodically, or the controller will periodically fetch the measurements from each and every device that he's communicating with. And in order to do that, we use the get measurements command. And here in this command itself, we'll add the multiple commands that we have defined in our address map. So the commands that go in here should be commands that are defined in your address map as well. So it can be as like get measurements. We have now, I started my session with only having one multi-read register, but I in fact have multiple here. I have measurements 1, and I'll have measurements 2 as well, all the way up to 4, sorry. So they're all ending with a question mark. So this is how you define the get measurements command. So what it will do is in one single command, it will read or try to fetch all these measurements. And again, note that these measurements individually contain a multi-read. So with only like 3 commands that we'll be sending to the converter, you will be reading this one. So 119 plus 118 registers, 47 and 46. So with only one command or with 4 commands, you'll be reading lots of registers here from your converter. As an example, what other commands that you can define in here is, let's call it an initialize, or let's call it a start, for example. So during startup, what you might want to do is when you start up your controller or when you when you're first adding or starting your converter, what you want to do is maybe set your control towards port 1 method to a certain register, to a certain method. So for example, you want to do this, or you want to set your port 2 voltage to, let's say, 350 volt DC. You can add commands here, and with just one single command that says start, you can bulk send these commands to your converter. So this is what the control map actually is used for, like bulk send these commands all at once to the converter in this case, or any other device. I mean, like I said, you can add more in here. There might be a register that is called fault state. So when you, oh, sorry. So the name is let's call it a fault state. So when you reach a fault state, you want to send all the commands that you've listed here in your fault state. So it might be, I don't know if even defined in here, but you might want to say, okay, when I reach the fault state, I'll do a control reset 1. There might be some other things that you want to do. You want to maybe disable your converter. This is something that you can do here and define here. Okay, that was the next step of creating or doing the file configuration. So what we've done so far is we've updated the devices.json file. So we've added this new converter, and we made sure that we listed the correct control map and address map in here. And then we went on and create these address maps, address map and control map for this device. So we have the address map in here that contains all the registers, both read and write, for this converter. And we have now defined as well, or a control.json file to bulk send commands to the converter. One last thing that I want to mention is here in the configuration file. It's also an important file here, especially for your local nets. So know that, for example, if you want to write your custom application, there is a way to interact with the converter, and that's because of the local nets connection. So actually on the controller at runtime, there will be a net server that will be set up, and any other device, any third-party application or your custom application can connect with your this device over the local nets. So for example, let's give it a password, and we're all set here. So the IP address is still okay. Username, you can type in the password of your PLCNX as well. You don't need that. It's not required. It's an optional parameter here. And add your MQTT broker. It should be the same IP address as the controller here. Okay. Then, so we've created, we've done step 3 and step 4. Now let's move over to step 5. So we've created this, or we've modified all of our files. We added new address map. We added new control maps. What we want to do now is pull these changes or move over these files to the controller. My controller right here at the setup is not connected to the internet. It's a local one here now. So I'll using option 2 in this case. So I'll do a manual upload using FileZilla. If you want to, and this is a really good example of how to use Git again, is if your controller is connected to the internet, it's really easy to set it up and connect your GitHub repo to the controller. This is again explained in the documentation as well. So file configuration, if you want to pull your changes to the controller, please go to this this page on our controller documentation, and here are all the steps to clone this repository onto your controller, where to clone it to, and how to add it here. Because you set it up once and then you can continuously do a git pull to pull your latest changes onto the controller. But for now, since my controller is not yet connected to the internet here, I'll using option 2. And let's go ahead and do that. So what I'm going to do, I'm going to use FileZilla in order to do this. And what I want to do here is in the top left section, I'll type in the IP address of my controller. I'll type in the username and password and port, which is port 22. I'll do a quick connect, and it will connect me to my PLC Next, which is right here on my desk. Then I'll have to go to Opt PLC Next, Apps Home, Data, and then our application. And this is where the etc folder that we've just modified should be dragged into. So it's as easy as dragging your etc folder over from the left-hand side to the right-hand side. Left-hand side being your local GitHub repo on my laptop. Right-hand side being the controller and in the correct folder directory. So it's as easy as copy and pasting it over. So now the etc folder also lives on my controller, and that's how it's done. Again, this step is also explained in the documentation as well. So I've explained that the git pull is already explained on the documentation as well. Same thing goes for the offline. So I've explained in this documentation how to use FileZilla, but I also explained how you can use WinSCP to do the same thing. Okay. So now our etc folder that we've just created is now migrated over to the controller. And the next step that we want to do is reboot the controller, and that will reactivate and re-upload all the files that we just created to the controller, and then it will be ready to start communicating with the devices. So in order to do that, simple way is you go to the web-based management of the controller. This is the internal UI provided from the Phoenix Contact controller. So you type in your username and password in here, which directs you to the home page. Easiest way here is to go to Cockpit on your left-hand side and use this button to reboot the controller. Again, what this will do, it will restart the controller, reactivate the OS, and at startup, it will load all the new files that we have just created and uploaded. So we'll wait for the controller to come back online, and then we'll start running our custom or small application to see if the controller is effectively communicating with converter 1 in this case, which is the 30C3 stability. So let me open this one. So this is a small application I wrote to verify that the controller is effectively connecting to the converter, and that it also is reading all the correct values, that it gives some values back, and all this. So we'll wait for the controller to start up again. It should be any second now, and then I'll try to run this application. So this local application that I've built here, it's also using that Nets client and Net server application that I talked about. So on this local, it's a Nets client that is trying to connect with the Net server that's running on the controller. and it's password protected. So the username and password should match in order to make sure that your local application is connected to the controller. So let's try and run this application. What it will do, it will just output the voltage, current, and power for each port. And I don't know if you mentioned this before, but it's a 3-port converter, one AC port, and port 2 and port 3 are both DC ports. So let's try and run this device measurements application. I'll make the screen bigger in order for you to see. So it connected to the converter, and you'll see the actual values that are reported back from this converter. So on port 1, we see like 469, current 1.6, and our power is 1500 watts. And then same thing goes for port 2. Port 2 is the one where our battery is connected to in this case. So it's 862 volts, 11 amps, and almost 10 kW. And port 3 is our DC bus running at 350 volts. It has a current of 21 amps and 7 kilowatts reporting. Okay, so this is an indication that our setup was successful. So we were able to change the devices or add this new device to our device.json file, create the address maps, create the control maps, and all uploaded to the controller. And the controller is now able to communicate over Modbus TCP/IP to the converter in this case. Okay, I think that's it for this demo. So we have completed all the steps here. So what is next? So again, feel free to explore the documentation that we've put online. There are also some guides and troubleshooting tips that might help you resolve some typical issues, such as communication errors, comms issues, but also scaling issues, for example. Another thing is, so we have now added the battery and the converter, but next thing what you can do is add more devices, so like the solar optimizers, a new battery, even pre-charge circuits, digital inputs and outputs. It's not what we talked about in this session, but you can also add more devices on your digital side, for example, to control contactors, to connect with LEDs to give you a signal what state your microgrid is in. And then, of course, another next step could be develop your custom application. So when you can take full control over your microgrid. But the develop the custom application is something that we will do in this afternoon, in the afternoon session, so which is held between 1 p.m. and 2:30. And there we will write a self-consumption algorithm as well, and we'll test it on the equipment here in our lab. That concludes this demo, and I'll open up the floor for some questions. Dusan, do you know if there are any questions from the audience that came in?
So can you show the receiver mapping that already exists in design?
Can you show the 30C3? So yeah, I've showed you what the actual 30C3 address map now looks like. I can go over quickly one more time. I don't know when this question was asked. Yeah. Let me go over it again. So I mean, this is the complete address map, and this can also be made available for you. So if you at some point need to interface with the 30C3, this is the address map that you can use. It is all the relevant registers already in here. So.
Is there a future roadmap for Decide to perform as a programming tool for the controller and components?
Yes, there is. So we're working on interfacing or making a connection between Decide, between Decide and the controller. So as a first step, what we did. So if I go to directenergypartners.com, under one of the projects that I've created, if it will open, is so as a first step. So right now, first step, what we did is push live data back to Decide. So Dusan and maybe Hill already talked about that we push all our measurement and our data to a cloud, which can be used for visualizations. So I'll show you quick. So we have already set a database and Grafana for visualization. This is something that we already have. So for example, I can show you what our actual lab right now is, how it is performing. So this is our visualizations, our historical data. You see we have our DC loads in here, all covered by our battery now. We have not so much solar, but that's what I'm seeing as well when I'm looking outside. So we don't have much solar over here. So this is what we had and have still. And then what we're now doing is migrating this over to Decide as well. So this is an exact single line diagram of our lab 2, which I also will be showing in our afternoon session. So what I can do now is, this is not yet made publicly available, but I can show you the live data. So our controller, besides pushing to our cloud, it also pushes to our to Decide back, and you can see here that effectively our battery is now discharging at 20 kilowatts, and it's powering the EV charger. The EV charger has a communication issue here, I see, so we cannot actually see how much it is drawing, but that EV charger has a communication issue. But you see that we effectively are discharging our battery here, 20 kilowatts. I don't know if it's visible. It's really rather small, maybe, but we're discharging our battery to provide or to support our loads. One being our EV charger, the other ones being our DC powered loads and DC powered fans in our lab. And you can also see here that our solar, though it is limited, is importing 2.8 kilowatts on one end optimizer and 2.7 and the other ones. We do have other end optimizers, but they are connected to lab 1, which is a separate one. But yeah. This is what we're working on, and as a next step, of course, is we have Decide, we have our design platform. What we want to do is start coding from here and creating the files in here, uploading the address maps, and do like an export to controller where you can just migrate over your single line diagram to the controller and start troubleshooting and working with it immediately. So this is on our roadmap, and as a first step, we already built in the visualizations, but yeah, we're working on this in the back end. Okay.
So so somebody who's interested in like uptime availability and digging into the information, how could they benefit? Yeah, from doing this and deciding the controller.
Yeah. Also, something that we've implemented here is that comes together with the live data. So the live data pushes data back to our Decide backend server and what we also do is provide uptime availability here on our Decide platform as well. So you can see for the solar optimizers, there might be a communication issue for like a brief second in here. That's why you see the 99.972. So you can click on the uptime availability of every system or every component here. For the EV charger, you'll see it might have had some communication before, but it's now. For the LG battery, we have a 99.99. and the converters here too. So yeah, decide. I mean, this is what we want to integrate as well, and the uptime availability is critical in most applications. So we want to make sure that this information is all available in Decide as well. Yeah.
Seeing your questions online.
Okay. Any questions here from? No. Okay. A little bit before schedule. But I think that's fine. We'll resume at 1 p.m. for the afternoon sessions, 1 p.m. Eastern. I know that are probably some other guys from different parts of the world. So 1 p.m. Eastern, we'll resume with the next webinar, the hands-on lab, which will be a custom application development. So yeah, see you there. Thank you so much.